talk, and thanks to the organizers for inviting me to give this talk. And as Dan said, I'm going to be talking about how we estimate melt fraction in magma reservoirs using Magnetotellurics, and specifically focused on how we can incorporate some thermodynamic constraints from the MELTS modeling software to better constrain our interpretations. And this is work that I've been doing along with some collaborators, Juliana Troch and Christian Hubert, who are both volcanologists or petrologists that are invaluable to this project. All right, so yeah, just a brief outline. I'll give some motivation for why we're doing this. And part of that motivation is showing an example of some of the pitfalls that can occur when you're trying to estimate melt fraction from MT. And then I'll try and make the argument that we can correct some of those pitfalls by incorporating these thermodynamic constraints from melts. And then I'll finish off with two case studies, one from Laguna del Maule, volcanic field in central Chile, and then another one from Udrunku volcano in Bolivia. And like any good science problem, when you try and correct one problem, you end up maybe opening a can of worms. So I'll talk about that at the end of the talk. So the motivation here is that we're using geophysics to try to image magma systems in the subsurface. And specifically, I'm focused on very silicic or rhyolitic systems that tend to be more explosive and larger eruptions that are more hazardous. And we can have lots of different conceptual models of what the distribution of magma is like underground. And a lot of them have some, mush region of partial melt or some region of a higher melt fraction magma underground. And we're trying to, again, characterize the size, the depth of these features, the location of the features, and also the melt fraction of these features. Just to get some of the terminology right, when I say a mush, I'm talking about relatively low melt fraction, partial melt, where the crystals are connected in a solid framework. So the mushes are much more viscous and don't erupt very easily. And so these are generally a little bit more stable. In contrast, we have a magma where the crystals become suspended in the melt and the viscosity of the partial melt drops significantly. And these are more able to flow easily and can be more eruptible and thus more hazardous. So it's important when we're doing geophysics, if we're trying to estimate melt fraction, to be able to distinguish between what would maybe be interpreted as a melt versus what would be interpreted as a magma. And just to kind of pin some numbers on here, no one really agrees exactly where these transitions occur, but you could have, 5% melt would be a melt poor mush, 25% would be a melt rich mush. And then you have this transition to magma at some point, maybe around 30 to 50%, and you end up with a crystal-rich magma at 60%. And of course, you could have a pure liquid magma at the far end of the spectrum with 90% melt. And again, I'm focusing mostly on silicic or rhyolitic systems here. So the question then is, how can we measure this with geophysical methods? And one way, there's lots of different ways, including seismic and gravity, for example, but the way I'm focusing on today is Magnetotellurics, or MT for short. And for those that aren't so familiar with the method, it's a natural electromagnetic method where we measure these natural variations in the electric and magnetic field at the surface of the Earth. And the ratio of those fields gives the impedance of the Earth, which is a frequency-dependent quantity, where higher frequencies sample shallow depths, maybe in the upper 100 meters or a couple hundred meters or so, and lower frequencies sample greater depths down to tens or even hundreds of kilometers depth. And because it's such a broadband method, it's really versatile for this broad range of depths of investigation. So once we do fieldwork and we collect this impedance data, we can invert the data to recover Earth's bulk resistivity structure. And that's kind of the quantity of interest, is the bulk resistivity of the Earth. And the bulk resistivity is useful to know, especially for volcano studies, because the bulk resistivity varies over several orders of magnitude. Here's resistivity up here, so from 10,000 ohm meters down to 0.01 ohm meters. Varies over several orders of magnitude for different Earth materials. And just the arrows here show materials that would be interesting for in volcanic settings, such as brines, geothermal fluids, pure melts or partial melts. And these are much more conductive than, dry granites or dry basalts. And so these are kind of the features that we're interested in detecting. And so we want to, if we see a conductive anomaly in our data or in our inversion model, we might interpret that as one of these things, either brines, pure melts, or partial melts. But we can try and be a little bit more quantitative rather than just saying, okay, well, there's a red low conductivity anomaly, that's probably some sort of partial melt. We can try and be more quantitative by actually estimating the melt fraction. So how much melt is actually present in that anomaly based on the bulk resistivity. Kind of the what I would call the standard approach to doing this. It follows this kind of workflow where you have bulk resistivity, which is what you're after at the end, and it can be estimated from all these different parameters. And there's a lot of parameters here. You got pressure, temperature, and dissolved water content, which are related to melt resistivity based on some empirical relationships. And then you've got the crystal resistivity, and you combine the melt resistivity and crystal resistivity into some sort of mixing relationship, which is based on either empirical studies or theoretical modeling. And from that, you can get the bulk resistivity. So again, this is a pretty non-unique problem, obviously, because there's one number that let's say from your inversion model, that an anomaly has, a resistivity of 1 ohm meter. But there's all these variables that go into that single number. So trying to tease out what's what is somewhat complicated. And again, just to remind you, kind of the quantity that we're really interested in from a volcanological perspective is the melt fraction. So we can kind of knock down some of these variables by just checking them off the list, since pressure, for example, has a small impact, and also our inversion model usually has a pretty good range of depths where the feature is located, so we can use depth as a proxy for pressure. Crystal resistivity has a really small impact on the bulk resistivity because it's generally assumed to be much more resistive than the melt resistivity. So it doesn't really impact the bulk resistivity too much. And then we can make some assumption about the network, the way that the melt is connected within the crystals. And here I'm assuming a Hashon-Strickman upper bound, which is a theoretical model of well-connected melt. Another popular one that often gets used in the literature is Archie's law or modified Archie's law. And between Hashon-Strickman and modified Archie's law, you get quite similar results. So by knocking those variables out of the equation, you are left with basically 4 variables that really matter. The bulk resistivity, which is you often know from the inversion model, the temperature, dissolved water content, and then the melt fraction, which is usually the variable that you're interested in. And so if you know any 3 of these 4 variables, you can always calculate the last one, or at least if you can place bounds on 3 of the 4, then you can place bounds on the last one. And so just to kind of convert this workflow into 2 figures here, what I'm plotting on the left is temperature and dissolved water content, and those can be used to calculate melt resistivity. And then on the right is melt fraction and melt resistivity, which can be used to calculate bulk resistivity. And this is using an empirical relation for rhyolites, and this is using the Hashon-Strickman upper bound. And so again, here's those 4 variables: temperature, dissolved water content, melt fraction, and bulk resistivity, all on the same plot. And I'm just going to kind of, for illustration purposes, to show some of the pitfalls of where things can go wrong, I'll just kind of make up some numbers that might be somewhat realistic, just to show how this all works. So let's say you have a magma reservoir where you have some estimate or some ballpark temperature of 750 degrees to 900 degrees Celsius. So you kind of know that from maybe petrological studies that have shown that, or just you kind of know based on thermal gradients or something like that, that you know that's what the temperature might be. And you also know that the magma reservoir might be 4 to 5 weight percent water. So from that, you can calculate the lower bound on the melt resistivity and the upper bound on the melt resistivity, and then plot those on the mixing relation graph as, again, the red lines and the blue lines corresponding to those same resistivity values on the x-axis. And so the last thing we need to know is the bulk resistivity. And let's just assume for a moment that we know the bulk resistivity from some inversion model is 1 ohm meter. And again, I can talk a lot about all the uncertainties related to getting that actual bulk resistivity from the inversion model, and I'll mention that a little bit later on in the talk. But let's just for a moment assume that we kind of know this really well, that it's 1 ohm meter, and you can plot that contour as this dark contour here. And so from this, you can pick off these two melt fractions at the blue dot, which is around 90%, and the red dot, which is around 38%. So that would be your final kind of interpretation, given all this, that you have a magma reservoir that's 1 ohm meter with a melt fraction between 38% to 91%. So the first issue that often crops up, and this happens in many different studies, is that this range is really, really large, right? I mean, 38% might be more of a mush that is quite viscous and not very eruptible, versus 91% is, an interpretation of essentially a pure magma. So the mechanical properties of these two melts are so different that it's almost like a useless estimate when you have a range so large. So that's the first problem. The second problem, which is maybe not as obvious, is that the hotter melt, the one at 900 degrees, which is this red dot here, corresponds to the lower melt fraction interpretation. And the cooler melt at 750 degrees corresponds to the higher melt fraction. And obviously we know just intuitively that a higher temperature should correspond to low or higher melt fractions, right? Because more rock melts as you get hotter and hotter, and lower temperatures should correspond to lower melt fraction. So there's a little bit of a weirdly unintuitive relationship going on here. And I'm just going to show that on the next plot by make it a little bit more clear by combining these two into one plot. You can see that melt resistivity is kind of a middleman, which just takes you from this plot to this plot. But it's not really a relevant quantity. We don't really care what the particular melt fraction or melt resistivity is. We're more interested in these other variables like temperature, melt fraction, dissolved water content, etc. So if we fix the bulk resistivity at 1 ohm meter, then we can kind of explore the whole parameter space. So again, if you have a anomaly in your MT model that's 1 ohm meter, then you can plot this graph here, which shows all the possible melt fraction, temperature, and water content combinations that are consistent with a 1 ohm meter anomaly. So you could say, okay, well, at 850 degrees and 4 weight percent water, you can kind of pick off the melt fraction here in the green color is around 60%. So this kind of shows the whole range of possibilities. And again, you can plot the same box here showing this 750 degrees to 900 degrees Celsius and 4 to 5 weight percent water. And you can pick off the same melt fraction, 38% and 91% down here. So it's just another way of showing the same information as the previous slide. But the way of looking at it here shows how certain parts of this parameter space are clearly wrong. I mean, even me as a geophysicist who doesn't really have much understanding of the melting of rocks, I kind of know intuitively that at 1,000 degrees and 5 or 6 weight percent water, a rhyolite will be probably 100% melt. It won't be 25% melt here. It won't be a mush. And similarly, at 650 degrees and 1 weight percent water, I also know just intuitively that a rhyolite will probably be very, very close to the solidus, if not subsolidus, under those conditions. Whereas this parameter space shows it as being 100% melt, which is clearly not a physically realistic interpretation. So clearly, some parts of this parameter space are not actually realistic interpretations. But it's not immediately obvious which parts are realistic and which parts aren't realistic. For example, is an interpretation of 38% melt at 900 degrees, is that a realistic interpretation? As without modeling it or without knowing it, it's hard to intuitively surmise whether that is a realistic interpretation or not. So that's kind of laying out the two pitfalls. There's the one which is more obvious, and that's just how do we make these estimates more accurate, right? We have this huge range of 38% to 90% melt, which is so massive that it's almost not useful. And then the second problem is how do you avoid these potentially unrealistic melt fraction estimates that just don't really make sense thermodynamically based on the temperature and dissolved water content. So those are the two issues. So how do we correct those? And the way that I'm proposing is to bring in some thermodynamic melting models. And we're using Rhyolite Melts here, which is a thermodynamic modeling software. However, it's, as a non-petrologist, it's quite a dense piece of software that isn't particularly easy to use. If I'm not sure if anyone here has used it before, but it has lots of knobs and takes some time to run as well. So I've teamed up with two collaborators I mentioned before, Juliana Troch and Christian Hubert, and they have developed a parameterization of Rhyolite Melts, which can be used in MATLAB and runs very quickly in order to explore the full parameter space very rapidly. And again, I'm not the expert on this part of the problem, but they're using a generic average rhyolite to run multiple simulations of melts, and then they fit it to some sort of parameterization in MATLAB. And by doing this, you can create these plots showing the kind of full parameter space of the parameterization with y-axis of temperature, x-axis of total system water, and then the colors are melt fraction. And this plot is divided into kind of 4 regions. You've got the superliquidus phase up here with only one phase, it's just pure melt. You've got the undersaturated partial melts, which have 2 phases of crystals and melts. And this is kind of the region that most of us, or most geophysical interpretations anyway, are kind of concerned with. We're often just interpreting 2 phases, crystals and melts, and we don't really think about the saturation problem. But below this black curve here, you've got oversaturated partial melts with 3 phases. You've got crystals, melts, and then a free fluid phase, which is in this case composed of H2O. And then up here, you've got the 4th 2-phase situation, which is saturated superliquidus, which I don't really hear people talk about too often. I don't know if that occurs very often in nature. And so you might automatically see that there's some clear similarities between this figure, which I showed before, which is derived from bulk resistivity, where you've got temperature, dissolved water content, and then melt fraction as the color. And then this one, which is derived from melts, where you've got temperature, water content, and melt fraction as the colors again. Except you can see that the colors are inverted, right? This one has that unintuitive non-physical relationship where melt fraction decreases with increasing temperature, which doesn't make intuitive sense. Whereas melts, because it's a thermodynamic modeling software, obviously has the correct intuition where if you increase temperature and you increase water content, you're going to increase the melt fraction. The only difference between these two is that on the x-axis here is dissolved water content. And so this whole workflow that I showed before implicitly assumes that the melt is undersaturated. So all the water in this system is dissolved in the melt. Whereas here you've got the possibility, instead of dissolved water in the melt, you've got the total system water. So that's how you end up with the saturated regime where water is not just dissolved in the melt, but it can actually form this 3rd fluid phase below. So you're very, very close to having something almost identical. The only thing you need to add here is the dissolved water content to this melts plot, and that can be also computed from the Rhyolite Melts parameterization. So the dashed contours here are showing the amount of water that's dissolved in the melt. And so you can see that as you increase the total system water, you get more water into the melt, obviously, as you'd expect. And also as you decrease temperature, you end up getting more water into the melt as well. And then you hit the saturation, which is around, at this particular pressure, it's around 5 weight%. And from then it's basically 5 weight% throughout the whole saturated regime, because all the extra water is getting dumped into this 3rd fluid phase, which is a free fluid phase. So you can see now that we have temperature on the y-axis here. We've got dissolved water content as the dashed contours, and we've got melt fraction as the colors. And if you remember, those are 3 of the 4 variables that you kind of need in that previous workflow that I showed. So we can actually calculate the bulk resistivity directly from these three variables using the exact same workflow as I did before. And the figure gets a little bit complicated, and I'm leaving the dashed contours, which are dissolved water content on here, just to show the full relationship between all the variables. But I've added now these solid contours for bulk resistivity. And so this is kind of putting it all together here, where you've now got bulk resistivity as a function of temperature, dissolved water content, and melt fraction. And these bulk resistivity contours are consistent with the thermodynamic models. And so you're not getting these unfeasible or unphysical interpretations based on a bulk resistivity. So if you have an anomaly in your MT model that's 1 ohm meter, you can look anywhere along this contour and make an interpretation about the amount of water content, the temperature, the melt fraction, and those are actually consistent thermodynamically, and you're not running into the situation where you have, interpreting 100% melt somewhere that is clearly too cold to be 100% melt. The elephant in the room here is that I've blocked off a huge amount of the parameter space. You can see that I've just said ignore saturated melts. And that's kind of sad to do, but I just want to remind you that pretty much all the interpretations that you see in the literature interpreting melt fraction from geophysical results, or at least in the MT world, are almost always using these empirical relations that assume the melt is undersaturated. So we're almost always in this undersaturated world anyway, and we don't really think about this part. So that's kind of the can of worms that I'll open at the end of the talk, is what do we do about the saturated melts? And again, so just coming back to this example that I had before, if you have a 1 ohm meter anomaly from 750 degrees to 900 degrees, and a dissolved water content of 4 to 5 weight percent, which is bounded by these two contours here, then you can interpret it, and you can see that where these intersect, the gray region and the white line is kind of where your solution would lie. And you can see that it actually constrains the potential parameter space quite a bit to this very small region in that blue box. And just zooming in on that, you can see you can pull off melt fraction estimates. Sorry, melt fraction estimates, high maximum melt fraction up here, and a minimum melt fraction down here at the saturation curve. And you end up with a melt fraction estimate between 62 to 80%. And this is less than 20 percentage points, whereas the previous estimate that I showed using the unconstrained resistivity only method rather than including melts had this range of it was 50 percentage points. Yeah, 50 percentage points from 38% to 90%. Whereas here now we've constrained it to less than 20 percentage points. So that's a pretty remarkable reduction in the amount of error. And not only that, we've actually also constrained the temperature a little bit better, whereas the previous interpretation made didn't say anything about temperature at all. It was still the original range from 750 degrees to 800 to 900 degrees. We've now constrained it to kind of the lower end of that from 760 to 780 based on these constraints. And the dissolved water kind of stays the same between 4 to 5 weight percent. So that's kind of putting it all together and showing how we can constrain this so much better by incorporating melts. Just returning to this figure, remember before that I asked, what areas of this parameter space are actually valid? Because obviously up here is not valid, and obviously down here is not valid, but it's kind of hazy what's valid in between. And so you can actually take this white contour, this is a fixed bulk resistivity of 1 ohm meter, and you can pull out the temperatures and dissolved water contents along that line and just plot that line on this on this plot. And this shows which interpretations are actually valid. Which interpretations are valid from like a thermodynamic perspective. So you can't have this interpretation of 38% at 900 degrees, because if you have a rhyolite at 900 degrees and 5 weight percent water, it's actually going to end up being almost 100% melt anyway. Whereas if you trace this curve through this parameter space, these are kind of the thermodynamically realistic or thermodynamically valid interpretations through that parameter space. So we really collapsed this parameter space down from effectively unconstrained down to a single line through that space. And that's kind of the major benefit here of including the constraint for melts. And again, you can pull off the same numbers just from this plot, just by taking this line as it crosses through this box, because this box is the bounds that we had. And you get the same numbers, 62% down here to 80% up here. And you're also constrained the temperature, as you can see. So that was kind of using just an example of a 1 ohm-meter anomaly, just to show the benefit very clearly, where you can constrain the melt fraction so much more by using melts. And I'm just going to walk through a couple case studies now. The first, again, is Laguna del Maule volcanic field in central Chile. And then the second one is Udrunku in Bolivia. So case study number one, we're located in central Chile. This is a rhyolitic system in the high Andes that's been active for about 1.5 million years. But in the last 25,000 years, it's had this remarkable amount of rhyolite that has erupted. Prior to 25,000 years ago, it erupted basalts or andesites, dacites, and rhyolites, whereas since 25,000 years ago, it's erupted pretty much only rhyolites. Not only that, but in the last decade or so, it's been experiencing this really rapid and ongoing deformation, with the center deformation on the southwest side of this eponymous lake here. And it's had almost 3 meters of uplift in a decade, which is really quite remarkable. There's been a lot of studies here, both mapping the lava flows and also analyzing them with petrology. And so based on that, we've kind of petrologists have constrained the magma reservoir temperatures and water contents to be between 750 degrees to 850 degrees Celsius and 4 to 5 weight percent. And so we went and collected MT data here about 5 years ago and did some modeling there. But here now I have to kind of address the problem of how do we get the bulk resistivity in the first place, right? Up until now, this previous example that I showed had just kind of this 1 ohm-meter hypothetical anomaly. And that was done just to try and ignore the problem of actually estimating the bulk resistivity, because they're kind of two separate problems. On the one hand, you have the issue of estimating the melt fraction from a bulk resistivity. And on the other hand, you have the problem of estimating the bulk resistivity from a MT data set or from an inversion model. So most commonly, people will use a deterministic inversion, which basically just gives you one solution. And that is basically single bulk resistivity value from which you then do your interpretation. But there's also some other ways that have been developed. And this algorithm that I'm using is from work that Dan Blatter did. And this is a Bayesian inversion, which inverts an MT site and computes the depth and resistivity with colors for probability. So instead of just giving a single answer, it gives kind of a distribution of models that all fit the MT data equally well. And so this is an inversion of a site just right above the inflation center. And what you can see here is that there's kind of a conductive layer that's relatively well defined here with bright colors indicating higher probability. Then you've got this diffuse resistive layer, another diffuse resistive layer down here, and then this really well-defined conductive layer between about 3 kilometers and 5.5 kilometers depth. And this is kind of the feature that we're interested in from a volcano perspective, where you've got this conductive layer, which is interpreted again as some sort of magma reservoir related to the ongoing deformation and inflation that's being observed there. And so again, instead of just getting one number for the bulk resistivity for this feature, you can now pull out the average bulk resistivity of this layer and create a histogram from the ensemble of models. And you get an average bulk resistivity for the conductive layer that has a distribution like this, with an average of about 4.7 ohm meters and a max and min. So this kind of gives you an idea of the uncertainty in the bulk resistivity estimate that you're getting from the NT data, which is really useful, because with only just a single solution, you would have no idea if it's, plus minus 10 ohm meters or plus minus 1 ohm meter, but this gives you fairly good confidence that the resistivity of this feature is actually quite well constrained. So once we have the resistivity, then we can kind of proceed with the workflow that I was showing in the previous example. But I had to do this little aside here to explain like how do we actually get that resistivity value in the first place. But once we have it, we have this distribution of resistivities. Then we can go ahead and interpret that feature using the two methods that I showed earlier. On the one hand, we have the bulk resistivity only estimate, where we can draw this box showing the temperature and water content bounds. And you can make an estimate of the melt fraction from this box using this plot. You can see that this plot is much more blue than the previous plot. That's because the resistivity is a lot higher at 4.7 ohm meters. So you end up with much lower melt fractions. And you end up with a value of about 11 to 25% melt fraction using this method. However, again, it's unclear whether these interpretations are realistic because you have 850 degrees and 5 weight percent water being interpreted as 11% melt, and you have a colder 750 degrees and drier 4 weight percent water being interpreted as a higher percentage of melt. So it's unclear whether these are actually thermodynamically realistic or not. So you can do the same thing with the melt constrained bulk resistivity. And in this case, the white line here is a 4.7 ohm meter contour. And again, it crosses through the gray region, which is the constraint from petrological studies. And you end up with, in this case, a melt fraction of 17% to 23% melt fraction. And you also get a better constraint on the temperature as well. Whereas here you're left with a range of temperatures from 750 to 850 degrees. Here you've actually constrained it a little bit to the kind of lower end or the cooler end of temperatures. And you've cut the uncertainty in melt fraction by about half as well. And not only that, but your interpretations are actually thermodynamically consistent with melting relationships. And again, you can plot the curve. It's basically plotting this contour onto this parameter space here. And you can see where it crosses through the region of interest. And you can also see why this red dot is actually not realistic, because at 850 degrees and 5 weight percent water, you actually have basically pure melt over here. So that's an example that really works out quite nicely for Laguna del Maule in Chile. It shows the benefits, but the benefits aren't massive per se. It is cutting the melt fraction error in half here, but at the end of the day, the interpretation as a relatively low melt fraction mush isn't really going to change. The second example is an example which kind of shows where things go a little bit wonky, I guess. And this is Udrunku in southern Bolivia. And this volcano is part of the Altiplano Puna volcanic complex. And it's overlying this magma body called the Altiplano Puna magma body, which has been well mapped using different geophysical methods. And it's shown by this dashed line here. It's this huge feature that's been imaged with seismic, gravity, and magnetotellurics. And Udrunku has had the most recent eruption was almost 300,000 years ago. So that's a lot longer than Laguna del Maule, obviously. However, just like Laguna del Maule, it's also showing signs of unrest, although not quite as dramatic as Laguna del Maule, but there's been this decades-long signature of ground deformation. And so some people are kind of calling this a zombie volcano because it hasn't erupted in so long and should be basically a dead, extinct volcano, but it's actually showing signs of life. And again, there's been lots of petrological studies of this volcano, and they have the magma reservoir, or the APMB, is estimated to be between 840 degrees to 980 degrees. And there's a really wide range of water contents from about 4 weight percent up to 7 weight percent. And some authors have pushed that up to 9 or even 10 weight percent. So it's an incredibly hydrous magma reservoir, or at least that's what some of the data seem to indicate. So we can do kind of the same workflow where we take some MT data that were collected at Udrunku and invert them using Bayesian inversion, and you get a similar sequence of conductors. It's just a different scale of depths. You've got a conductor in the near surface, just like at Laguna del Maule, and and then this very, very large, kind of poorly resolved resistive region, and then a much more tightly constrained conductive layer around 15 to 25 kilometers depth. And again, you can pull out the average bulk resistivity from this layer and create a histogram of resistivities for that conductive layer. And what you end up with is a conductivity of this layer of 0.61 ohmmeters. And if you remember from Laguna del Maule, the conductivity was 4.7. And so this is quite a bit more conductive. It's almost an order of magnitude more conductive than Laguna del Maule. And that's very, very surprising. And this is actually very similar to what was observed with 3D MT modeling. So this is an image of a 3D deterministic inversion. So again, it's just one solution, not a Bayesian inversion where you're getting a distribution of solutions. But you can see here, this is the APMB down here, and it's basically going off the color bar scale, right? The minimum resistivity here is 1 ohmmeter, and you're getting sub 1 ohmmeter resistivities. And in their interpretation in this paper, they just used a value of 1 ohmmeter to characterize this because they didn't really know how conductive it was, and they just wanted to pick a value that was kind of reasonable because 0.61 is quite conductive. So how does that kind of map onto this space if we take bulk resistivity only interpretation using this fixed 0.61 ohmmeter anomaly? You can see it covers a pretty broad range of the parameter space because the water contents range is so large, from 4 weight percent to 7 weight percent. And as a result, you get this correspondingly massive range of melt fractions from 31% to 100% melt. And because we're kind of averse to interpreting magma reservoirs as very high melt fractions, it would be probably common to end up stating that, oh, this is around 31% melt. And that's especially true because some of the seismic results from the APMB have shown melt fractions around 25 to 30% as well. So saying that this feature is 31% melt kind of jives with that. But remember that 31% melt is using a temperature of 980 degrees at 7 weight percent water. So is that actually thermodynamically realistic to have that kind of melt fraction at that temperature and water conditions? And so we can map that onto this melt constrained bulk resistivity space. And you can see that here's the white line showing the 0.6 ohmmeter contour. And you can see that this gray box showing the kind of area where petrology would suggest you are is basically all superliquidous temperatures and water content conditions. And the 0.6 ohmmeter contour does pass through the box, the constrained area, but it basically requires that you have 100% melt at these conditions, which again is probably quite unlikely to have this large volume of magma completely molten, right? And again, you can map this onto the space here, showing these valid kind of or thermodynamically realistic interpretations that follow along this line here. And anything outside of that, especially if you stray really far from this line, probably starts to become unrealistic or physically difficult to explain. So in this case, we have this kind of mismatch, or at least some confusion when you include the melts constraint. You realize that, oh, this actually has to be basically 100% melt given all the constraints we have. Whereas here you might end up erroneously making kind of a unfeasible or unphysical interpretation that this is a 31% mush. Whereas here you're like, okay, well, this has to be 100% melt, which doesn't really make any sense. So what's kind of the explanation? What has to give here to explain this? And one possibility that I would throw out there is maybe these temperature and water content ranges are from, well, they are from, the last eruption was 300,000 years ago. And so perhaps the system has actually cooled a little bit and you've been pushed down into this region here. And as you can see, the contours kind of turn quite sharply. It's this very nonlinear problem, which I find really interesting. But if you end up pushing the temperature down, you end up approaching the saturation line, and you end up with melt fractions which are much more kind of reasonable, and you can get down to melt fractions as low as 25% or 30% down here on this end of the white line. So those are kind of two case studies to look at and showing how we can better constrain the melt fraction and also realize when our interpretations aren't actually physically valid. So remember, there were two issues I was looking at, and I think we've managed to constrain those estimates a lot more and make them more accurate. You know, using the standard approach had 50 percentage points or more, 60 percentage points spread in melt fraction estimates, and we can cut that down considerably using this melts coupled approach. And it also has the benefit of resulting in these thermodynamically consistent melt fraction estimates that aren't unrealistic. And as an added benefit, it enables more quantitative temperature and water content estimates as well. You can actually constrain the temperature better too. Now, the can of worms that I kind of alluded to way back at the beginning is what about the saturated melts? Throughout this entire time, I've been just conveniently blocking this whole part of the parameter space off. And this is kind of the can of worms that is difficult, or that we don't really want to open. Most of the interpretations that you see in the literature, all geophysical interpretations anyway, all assume that you only have two phases, that you're kind of in this undersaturated regime where you've just got crystals and melt, and it's a lot simpler. But once you start talking about saturated melts, it gets a lot more complicated, and there's problems with trying to characterize saturated melts. The first problem is that we don't know the resistivity of the fluid phase, especially from a resistivity, from an MT perspective. We really don't know how to characterize it. We don't even know if it's necessarily supercritical or not. And this involves some really complicated equations of state that haven't really been explored, at least for this particular application. We also don't really know anything about the salinity of the third fluid phase. A lot of the melts program, gives you the free fluid phase, but it assumes that it's basically pure water with no interaction with the crystals. There's no dissolved ions in the fluid phase at all, so we can't really characterize the salinity. But we often know from, for example, geothermal drilling, that the fluid phase, the fluids that come off these magma reservoirs can often be hypersaline. So if it's a supercritical fluid, you might end up having a resistive fluid phase, whereas if it's a supersaline brine, you might end up having a conductive fluid phase, and it's really not very well constrained. And then the third problem is that the second problem is that three-phase mixing laws are quite complicated. You have additional problems of immiscibility between the fluid phase and the melt phase. You've got additional complexities with the network topology, and it just is kind of a can of worms that hasn't been studied very thoroughly, at least to my knowledge. But just to throw it out there, I'm going to plot the kind of two end members. The first is a conductive end member where you've got a very conductive brine, basically of 0.1 ohm meters, and you can kind of see how the contours behave in this scenario. If you have a 0.6 ohm meter anomaly and it crosses this boundary between the undersaturated and saturated fluids, then you kind of get this shape. I'm not really going to explore what that means, but I'm just showing that it can be done, and this is using modified Archie's law for three phases. And then the second end member would be a resistive end member, where let's say you have this very resistive supercritical fluid that's 100 ohm meters. And in this case, it kind of shoots off horizontally the contours. You can see they basically just follow the contours of melt fraction at that point. So you can explore this space, but it's just a big unknown basically as to how what the bulk resistivity might be based on the resistivity of the fluid phase. And so yeah, I'll leave that up there as kind of a question for future work that I think would be very interesting to explore further. And with that, I'm happy to take any questions that anyone has. Thanks so much.
Thanks, Darcy. That was really amazing. Thanks for all of that. That was a very complicated topic laid out very clearly. And I think you've brought to mind a lot of interesting complications that I don't think we're, as a community, we're not quite at the stage where we can deal with them properly. So that was really awesome. Thank you for your presentation. Does anyone have a question they'd like to ask? Just sort of feel free to raise your hand either through Zoom or just unmute yourself and ask away.
Well, maybe I should jump in just to break the ice. Lovely talk, Darcy. Sorry I couldn't be at the beginning. I had another meeting I had to go to first. The Bayesian inversions, or the stochastic inversions, I prefer to call them, tightly constrain the resistivity, and presumably was having to rely on a 1D assumption.
Yeah, that was a 1D inversion. Yeah.
So it's nice to have the uncertainty estimate, but do the deterministic inversions really end up with very different resistivities?
No, they don't actually, to be honest. I showed the one, let me see if I can go back. Oh, it doesn't matter. I showed the one how it actually matches. Well, it kind of goes off scale, unfortunately. The one from Udrunku, the minimum resistivity that they plot is 1 ohm meter, and the whole anomaly is basically red. So I'm actually not sure. I'd have to go look at the actual model to know what the minimum resistivity of that feature is, but presumably, yeah, it's kind of around maybe 0.5 ohm meters or something like that. And then for Laguna del Maule, it also matches quite well as well, within, plus minus 1 or 2 ohm meters.
Yeah. Okay, thanks.
Gina had her hand up.
Oh, yes. Thank you for the great talk. I really liked it. And I am not really an expert in this area, so I have a question about the bulk, not constrained model, just using only the bulk resistivity. So I see that it's not really intuitive, as you mentioned, but I wonder why the model is kind of widely used, or is it have any strong point in other aspects?
Let me just go back here. So you're kind of talking about like this plot as to why it is the way it is, I guess.
No, I mean, like, why is the plot is it widely used in other subjects, or why is it not?
So the workflow that I showed at the beginning is kind of the way that we estimate bulk resistivity generally. So we, at least for volcano studies, we have the melt resistivity and the crystal resistivity, and we combine those into some sort of mixing model. And the reason that it's unintuitive is because as you increase the temperature and increase the water content, the melt resistivity goes down. So you actually end up getting much more conductive melts at higher temperatures. And so you need less of it to explain the bulk resistivity. So that's why the melt fraction goes down as you increase temperature and increase water content.
Oh, so I was kind of curious about why is that graph, it looks like, why is that so unintuitive? I mean,
why is it unintuitive?
To look like that?
So I guess the inconsistency occurs because you assume that you're implicitly assuming that the mixing relation and the melt resistivity relationships are independent. That's where the inconsistency occurs, because you're assuming that melt resistivity is a function of temperature and water content, and then you're using that to compute the melt resistivity, but then you're feeding that into the melt fraction estimate. But melt fraction is also a function of temperature and water content.
Oh, I see.
That's kind of where so we're kind of assuming that these two empirical relationships are independent when they're actually not.
Oh, okay. Okay, thank you. That helps a lot.
And maybe I can just piggyback. I see you there, Chenza. Maybe I can just piggyback on Gina's question real quick, Darcy. If it's so counterintuitive, why is it that the method on the left is still so commonly used?
That's a great question. And I think it's just because that's the way that people have been doing it. You have these empirical relationships that basically some laboratory experimentalists melt rocks and estimate the melt resistivity using that. And then we have these independent mixing relationships that often come from different fields, actually. I mean, I think Archie's law was originally applied to oil and gas, but it's still valid for mixing relationships for melts, but melts are just different than oil and gas, because oil and gas, you don't have this additional issue of the phases interacting, I guess, as a function of temperature and stuff like that. So
we've been combining different sort of tools and empirical relationships from different fields and sort of combining them without necessarily thinking too closely about the petrological relationships.
yeah, and I think that kind of hits the nail on the head. It's just thinking about the petrological relationships is important, I guess. But it's actually true that once you kind of see this, you start looking at other interpretations in the literature, and you're kind of like, oh, that actually doesn't necessarily make sense.
Well,
Thanks,
not only
Dan.
that,
That was exactly what I wanted to ask.
yeah, and not only that, Darcy, but once you start really poking into these details, you start, like you were mentioning, noticing a whole other can of worms that goes even another step further. So it's,
Yeah.
anyway, Jinza.
Thanks. Thank you so much, Darcy, for the wonderful talk. My question is, so in your example of Udrunku, the second one, you mentioned that the melt fraction suggested by the seismic studies seem to be a lot lower than the ones derived with MT. If that's true, do you have any comment on that?
There could be two things. So first of all, seismic, and again, I'm not a seismologist, so I'm not an expert, but my understanding is that seismic, the melt fraction doesn't, the seismic velocity doesn't depend on temperature or water content in the same way. It's more of just a straight conversion from melt fraction to seismic velocity. So on the one hand, you kind of avoid these additional complications that you end up with MT, but on the other hand, you also can't really get any estimate of volatile content, which MT can give you. So they're kind of complementary in that sense. And then the second possibility is just due to smearing effects, you could end up getting a much lower velocity than is actually there because of the smoothing and the smearing in the inversion.
So in other words, you think MT is better at constraining melt content than seismic, at least in this example?
I don't want to say better. Yeah, I think they just do, they perform different functions, I guess. I think the MT is really important in that it's able to get some estimate of temperature and water content, whereas the seismic, as far as I know, can't really do that in the same way.
All right. I guess a follow-up question on Udrunku is that, so it looks like you are getting really high melt content for this example. Is that really, dynamically stable? If you have, close to 100% melt in the magma chamber, why doesn't like erupt immediately?
Yeah, maybe I should have clarified that this is I'm basically showing that something is weird. And
okay.
this can't be, yeah, I'm not at all interpreting this as, okay, this is 100% melt fraction. I'm saying that something about the constraints or about the MT has to give to make this lower, because it's just so unlikely that you have 100% melt, right? And so what I was saying is that perhaps these petrological estimates of temperature are too high because maybe the system has cooled in the last 300,000 years. And so you're actually sliding down you're basically extending this gray box down into this region here, where you end up with much lower melt fractions.
Okay, thanks.
Yeah, just to follow up on that, sort of one of the frustrating things of doing what Darcy's been doing, which is like really sort of carefully teasing out all of the different petrological relationships and sort of trying to deal with them all in a holistic way, is that the problem becomes extremely nonlinear. Like if you look at Darcy's plot on the right there, between, I don't know what that is, 725 and maybe 800 degrees Celsius, you can go all the way from just a few percent melt all the way to 100% melt. So that you sort of rapidly enter a regime where you need really, really good temperature and water content constraints, which obviously we can't always have that good of constraints on. Yuri.
Yes, I have a question about the melts calculation that you used in the beginning as an example. So perhaps you could go to that slide. Yeah, like this one. Or before. Yeah, this one. So I realized that the calculation was done by somebody else, but perhaps you know the answer. I'm curious as to why the melt fraction is actually going down at the highest end of the assumed temperature and the water contents. So in that upper top corner on the right.
Over here?
No, on the right.
Oh, just this little corner right there?
Yep.
Oh, good eye. Yeah. That is because you have entered the saturated regime. And so there's a third fluid phase, which is taking up some of the fraction. So this is still 100%. Well, there's no crystals up here. There's no crystals, but because there's now a fluid phase, you end up with non-100% melt.
Okay, so it's not a solid phase, something else is.
No, yeah, this would be a
reducing.
fluid phase. That essentially you're getting to the point where this is like 10%. I don't actually know, 5% fluid, something like that.
Okay. And also have a comment about this inferred melt fraction for Udrunku. So models of deformation there suggest, at least some models suggest that there may be an active diapir growing on top of the Altiplano Puna magma body. And if that model is correct, it assumes that, or it implies that the buoyancy needed to drive the diapir that produces the observed surface deformation has to be proportional to the density contrast between the material inside the diapir and outside of that diapir. And the required buoyancy really suggests that the melt fraction has to be almost 100%. So it may not apply to the entire Altiplano Puna magma body, but at least that fraction or that portion of it that produces the surface uplift may well be almost completely molten.
Okay, yeah, that's interesting. Is that published somewhere?
Yes, I can send you the paper. It was 2012.
Okay, yeah, thanks. Yeah, that's interesting. Again, I think it would probably make sense maybe if you have an active diapir going on to have 100% melt, but I think the idea of having like the whole thing being 100% melt is probably not as realistic.
Okay, thank you.
Well, we are past the canonical hour. So let's thank Darcy once again, and we'll see you all next week.
Thanks, everyone.